Okay, now here's my answer to the three-part termination argument for the carpet. The base case is, again, is s less than cutoff. The reduction step is divide s by 3. And the argument, again, is as long as cutoff is greater than 0 and s starts greater than or equal to 0, repeated division by 3 will eventually reach base case. Great, there we go. That's two three-part termination arguments. Seems pretty easy, right? Let's go back over here to termination starter and do the three-part termination argument for hailstones. And what I'll do is I'll bring it up to right next to the hailstones function. What's the three-part termination argument for hailstones? Well, let's see. The base case is that n is 1. And the reduction step is, what's the reduction step? Well, it's right here. In this case, I can't quite pull it directly out of the code, but it's if n is even, then n over 2. If n is odd, then plus 1 times n3. That's the reduction step. So now we need to argue that the repeated application of the reduction step will eventually reach the base case. Well, you know, this first line looks pretty good. N keeps getting smaller, and if I'm going to argue that n reaches 1, n getting smaller all the time is good news. But on this next line, n gets bigger. It multiplies by 3 and adds 1. This could be hard. And in fact, this is hard. It's extremely hard. It's so extremely hard that the mathematicians haven't been able to prove it yet, and they've been trying for years. And that's despite the fact that no one has ever been able to find a counterexample. No one's ever been able to find a number n such that if you do the hailstone sequence on it, you don't reach 1. Every number n that they've tried always reaches 1. But no one has a proof that every number n will always reach 1. The reason I'm showing you this trick problem is to show you the importance of termination arguments. The two termination arguments we did over here in fractals were so simple that you might have thought termination arguments are always simple. And they're not always simple. They're both essential. Because we have generative recursion, we don't know whether these functions are going to stop without a termination argument. So they're essential. And while they're sometimes quite simple, like they are in the triangle and the carpet, even simple functions like hailstones can sometimes have termination arguments that are so hard that they're not possible. Now, this is a bit of an extreme case. In the functions that you're going to write, you're unlikely to encounter termination arguments that are impossible to prove. I'm just showing you this example as a way of helping you see that the termination argument can be hard and it is worth doing. Usually termination arguments are going to be quite possible, and they're often going to be a little bit harder than the ones in fractals. And we'll see some of those in the remainder of this material on generative recursion.